Hello, I am Lucas Gerin, and I'm doing probability at École Polytechnique near Paris. And I'm very happy and proud to give a presentation at Permutation Patterns 2021. And so I will review some recent works with Frédéric Bassineau, Mathilde Bouvel, Valentin Ferret, Michael Mazoun, and Adeline Pirot. Adeline and Mathilde already gave presentations at Permutation Patterns, so I will try to focus on the more probabilistic aspects. So basically, I would like to convince you that we have quite a general and powerful framework to analyze patterns in some random uniform permutations in a given class, as long as the class is substitution closed. Okay, and well, everything is better explained on the example of separable permutations on this particular class. So let's start with separable permutations. So first, I will tell you about separable permutations. And the trees. Okay, so I need a few definitions. So most of the time I will present permutations with their diagrams, and maybe you're familiar with direct sums and skew sums of permutations. So the diagram of sigma plus sigma prime is the diagram of sigma and sigma prime in the increasing order, while the diagram of sigma minus sigma prime is the diagram of sigma and sigma prime in the decreasing order. Okay, and I say that sigma is separable if and only if sigma can only be written with the trivial permutation 1 and the binary operators plus and minus. Okay. So here is an example. So for instance, 1 minus 1 plus 1 plus 1. 1, 2, 3. Well, by construction, it's separable. And let's see its diagram. So this is 1 minus 1 minus 1 plus 1 plus 1. So this is 5, 4, 1, 2, 3. Okay, and the counter example. Well, 2, 4, 1, 3. Well, you can check that 2, 4, 1, 3 is not separable. Okay, in fact, we have a criterion which says that sigma is separable if and only if sigma avoids both 2, 4, 1, 3 and 3, 1, 4, 2. Okay. So the big question we ask is, if we fix a small pattern pi, how many times does pi occur? As a pattern in a typical large separable permutation. Okay. So this is my main goal. And I will make this more rigorous. So to do so, it's more convenient to encode separable permutation with trees. So let's do this. So let's take my favorite example, 5, 4, 1, 2, 3. So as I said, this is 1 minus 1 minus 1 plus 1 plus 1. Okay. As sigma is built from binary operators, it's naturally encoded with a binary tree where internal vertices are decorated by this operator, plus or minus. Okay. So here, this is 1, 5, 4, 1, 2, 3 is 1 minus this big permutation. So this permutation is encoded by this tree, this binary tree. So at the root, I put a minus, okay, which comes from here. So it is minus the trivial permutation 1. And the right-hand side is this permutation. So this is my 1 minus, and now this one. So this one is plus 1 plus 1, 1. All right. Okay. So this one corresponds to this leaf of the tree. This one corresponds to this one. This one corresponds to this leaf. This leaf. This leaf. Okay. So now the issue is that, well, this encoding is not unique because essentially plus and minus are associative. Okay, so in order to have a unique one-to-one encoding, I have to gather as much as possible all the neighboring pluses and all the neighboring minuses. Okay. So in fact, this tree, this permutation is also encoded by this tree. So I gather as much as possible minus. So at the root, I have a minus 1, 1, and this subtree. And I gather as much as possible the pluses. So here, okay. So this is not a binary tree anymore, but at least the encoding is unique. Okay. And well, I can sum up things in a theorem. So if I understand well, it should be attributed to Bose. Well, there is a one-to-one encoding, so there's a bijection. To a separable permutation of size n, between the set of separable permutations of size n, and the plane trees with n leaves, because one leaf corresponds to 1 point in my permutation, okay, such that internal vertices are decorated with plus or minus, okay? And if we want the encoding to be unique, we impose that we have never two neighboring pluses or minuses. So I will say that in short, pluses and minuses alternate. Along each branch of the tree. And the out degree of every vertex in the tree well, it can be 0 because you have leaves in the tree. It can be 2 or more because you're starting from a binary tree. But the out degree is always different from 1. Okay. Okay. And such trees are called Schroeder trees. So I will denote by Schre of sigma. So this will stand for the unique Schroeder tree associated to sigma. Okay. So now this is nice to do combinatorics and probability to have this one-to-one encoding. But what about patterns? Because I said that I'm interested in the number of occurrences of a given pattern pi in a large separable permutation sigma. Okay, so what about patterns? So for instance, so let's take a very simple example. So let's say I want to compute the occurrences of the pattern 2, 1 in my favorite permutation 5, 4, 1, 2, 3. So this is just the number of inversions in 5, 4, 1, 2, 3. Well, there are 7 of them, if I'm right. 1, 2, 3, 4, 5, 6, and 5, 4. Okay. So so this is 7. So how can I recover the fact that there are 7 inversions in the permutation directly on the tree? So my tree is this one. So for instance, the permutation 5, 1 here. Well, 5 corresponds to this leaf, 1 corresponds to this one. And so the fact that there is an inversion between 5 and 1, so between the image of 1 and 3 by the permutation, just means that the subtree induced by these two leaves encode for the pattern 2, 1, which is the case because this subtree is only reduced to this binary tree with 2 leaves, which encodes the pattern 2, 1, because you have a minus. Okay, so the number of occurrences of pi, more generally, the number of occurrences of pi in sigma, it's just the number of subtree. So a kind of proposition. The number of occurrences of pi in sigma is the number of subtrees of in the tree Schroeder of sigma induced by k leaves, where k is the size of pi, which encode for pi. Okay. So my big question was, how can I estimate the left-hand side, the occurrence of pi in sigma? Well, sigma is typical and large. Well, I have to estimate the number of subtrees of size k in a large Schroeder tree, in a large typical Schroeder tree. Okay. So now I can tell you about our result, at least in the case of the separable permutation. So 2 patterns in separable permutations. Okay. So basically, at a very high level, the point is that Well, if n is finite, you have a Schroeder tree of size n. With decorations, minus, plus, and so on. And the main idea is that when n goes large, well, in some sense, a large Schroeder tree looks like a continuum fractal object, a continuum fractal tree, which is called Aldous continuum random tree. Okay, so this is a continuous and fractal tree. Called Aldous continuum random tree, which was introduced by Aldous in the beginning of the 90s. Okay, so this is a very broad picture, but hopefully we can, from this convergence, which is true in a sense, then one can deduce asymptotics for the occurrences of pi in sigma n. One hopes to deduce asymptotics for the number of occurrences of pi in sigma, for a sigma of separable permutation of large size. Okay, so it's time for a more rigorous statement. So here is the theorem. So from us, so Frédéric, Mathilde, Valentin, and Adeline. So we fix a pattern, so typically a small pattern. So fix K and a pattern pi of size K. We consider a sequence of random uniform separable permutations. So let sigma n be uniform separable permutations. And each sigma n is of size n. Then for every pi, for every pattern, there exists a random variable lambda pi in 0, 1, such that, so we consider the number of occurrences of pi in sigma n. So this is an integer valued random variable. So it takes its values between 0 and n choose k. So if I divide by n choose k, and I let n tends to infinity, then the left-hand side converges in distribution to lambda pi. Okay. And we will see that somehow lambda pi is related to this Aldous continuum random tree. Okay. So what can we say about lambda pi? First, if pi is not separable, you cannot find pi in sigma n. So this is useless, right? So the left-hand side is always 0. So, but what can we say if pi is separable? Well, lambda pi is strictly between 0 and 1. which means that the number of occurrences of pi in sigma n really scales like n choose k. And n choose k is about n to the k factorial k. Okay? And besides, lambda pi, still in the case where pi is separable, lambda pi is a true random variable. Okay. So for every pattern, this is the right scale, n choose k. We don't know much about lambda pi, but we have a probabilistic description which allows us to compute a few things. So first, in theory, we can compute the expectation of lambda pi for every pi. So informally, well, the expectation of lambda pi is more or less the proportion of subtrees of size k in the continuum random tree, which encode for pi. Okay, and in fact, we can do explicit computations with the CRT, with the continuum random tree. So we get that the expectation of lambda pi is the number of binary trees of size k which encode pi, divided by the number of binary trees with decorations, so which is Catalan sub k minus 1, which is the number of plain binary trees, times 2 times k minus 1, which corresponds to the number of ways of making decorations. Okay. And well, unfortunately, so as I said, we know very few things about lambda pi, and even in the very simple case of the simplest pattern, which is just 1, 2, we don't even know if lambda 1, 2 has a density. We don't know. We know almost nothing about lambda 1, 2, but we can have complicated recursive formulas which allow us to compute the first moments of lambda 1, 2. Up to the expectation of lambda 1, 2 to the 7, I guess. Okay, so in the proceedings, I put the first values, which are rational numbers, but which do not seem to be known. Okay, so I will try to give you a probabilistic representation of lambda pi in a very informal way. So probabilistic description of lambda pi. Okay, so let's take a sample of the CRT, the continuum random tree. So let T be a sample of the CRT, of Aldo's CRT. So it's a fractal tree, so obviously it's complicated to draw it with a pen. Something like this. Okay. With decorations on in each internal vertex. So we draw fair. So we use a fair coin to draw fair plus or minus fair means each plus or each decoration is plus or minus probability 1/2, 1/2. We draw fair plus or minus on each internal vertex. So let's say that the root is plus, plus, minus, minus. Okay. And now I do the same as in discrete. I take, so if pi is of size k, we fix k, we fix k, we fix pi. And we draw k leaves uniformly at random in the tree. So let's say L1, L2, L3. We get a subtree of size k. And lambda pi is just the probability that these k uniform leaves induce in capital T a tree which encodes pi. Okay, and this conditionally on the tree and on the decorations. Okay, so this is a random variable since it depends on T and on the decorations. And I should say at this point that decorations are independent from the tree, conditionally on the tree, and the leaves L1, Lk are somehow independent of the tree, conditionally on the tree. Okay, and so you see it's between 0 and 1 because it's a probability, and it's a random variable because it's a function of T and the decorations. Okay, and this probabilistic representation allows us to get some complicated recursive formulas for the first moments of lambda pi, at least for lambda 1, 2. Okay. All right. So at this point, we realized that somehow we needed a higher level description of the convergence to get a deeper understanding of the behavior of separable permutations. So this is what we should call the convergence as permutants. Okay. So permutants, they were introduced by Hoppen and et al. In 2014. And in a nutshell, a permutant is a limit of rescaled diagrams of permutations. So again, let's take my favorite example, 4, 5, 1, 2, 3. What do I mean by rescaling the diagram? So the diagram of 5, 4, 1, 2, 3 is the diagram of size 5. So I rescale it by factor 1 or 5. So I get a picture in the unit square. And I want to get a probability distribution on the unit square, on the unit square. So I put a mass 1 over n, so 1 over 5 in this case, on every square of size 1 over n times 1 over n, which corresponds to a point in the permutation. So here, so 5, 4, 1, 2, 3. So I put mass probability 0 here. And here I put uniformly in this small square a probability 1/5. Okay. So now this is a probability measure on the unit square. And this is the permutant associated to sigma n. Okay, so more generally, a permutant Well, this is just a probability measure. On the unit square. And since we want to generalize permutations, we want, since we start from permutation, you see that both projections along both axes are the uniform measure. So it's probability measure for which both margins, both projections, if you prefer, are the uniform measure on 0, 1. Okay. So now here is our result in the settings of permutants. So broadly speaking, this is the very same statement. So again, let sigma n be a sequence of uniform separable permutations. And for every n, let capital P sub sigma n be the permutant associated to sigma n. Okay. Then the sequence of permutant P sigma n. So here there is no need for rescaling because permutant is already rescaled. So it converges when n goes to infinity in distribution in the space of permutants So here I need to put a topology on the space of permutants, but permutants are just probability measures. So I can put the weak topology on the state on the space of permutants. So it converges to some permutant that we denote that by mu to the 1/2, where mu 1/2 is a continuous and fractal permutant. And well, as you might guess, mu 1/2 is related to Elders continuum random tree. And here, so you see that there is a parameter 1/2, which means that in my permutant, so I will explain this more precisely, but we take a CRT and decorations are fair on internal lattices. So pluses and minuses occur with probability 1/2 and 1/2. Okay. Okay, and so more or less, so very informally, mu 1/2, well, it's the pre-image of the Schroeder transformation from permutation to tree applied to Aldous CRT. So it's Schroeder -1 applied to Aldous CRT with fair pluses and minuses. Okay. And in fact, this was made rigorous by Michael Mazoun in 2019, I guess. Okay. All right. So this is basically, it's another formulation of the same result, but maybe at a higher level of description. Okay, so now what about universality? So I told you about the results for separable permutations, which are very nice because they are simply described by these very simple Schroeder trees. So we can ask, how can we generalize this kind of results for other permutation classes? So the first point is that we have to restrict to substitution-closed permutation classes. So we consider only substitution-closed which means that if theta of size k, pi 1, pi k belongs to C, then the substitution of pi 1 and so on into theta still belongs to C. Okay, in this case, well, uniform permutations in C can also be encoded with trees decorated with pluses, minuses, and simple permutations. Then we also can encode permutations in C with more complicated trees. Okay. Now the second point is that if in C, the family of simple permutations do not grow too fast, if simple permutations in C do not grow too fast, I mean the cardinality of the simple permutations in C does not grow too fast, then these decorated trees are still well approximated by Aldous CRT. Okay, and then in this case, so we have this combinatorial condition on C that is substitution closed, and this somehow analytical condition, which is that the family of simple permutations does not grow too fast. Then under so these two assumptions, we still have so again Frédéric, Mathilde, Valentin, Michael now, Adeline, and myself. So 2020. Then let sigma n be uniform in C of size n. Then the permutant associated to sigma n converges in distribution in the space of permutants towards mu, perhaps with another parameter. Okay, so here, this is very informally the permutant corresponding to Aldous CRT decorated with unfair pluses and minuses. Okay. So thank you. So I think it's time to stop. So thanks for your attention. And I'm looking forward to answering your question on the virtual workshop. Okay. So see you soon.